Welcome to the nitration of acetylonide and methylbenzoate lab. This is lab 5. So why is nitration so important? Well, it can be used in total synthesis. So for example, this product is an anti-tumor agent, and in order to get to this final product, they started with this starting material, and from this they did a nitration in order to get this product. And after many other steps, they got to this final product. So that's pretty cool. And so in order to explain nitration, we need to first go over electrophilic aromatic substitution, because that's how nitration happens. And as you guys know, E+ is an electrophile, and when that E+ has some sort of nitrogen in it, then that's when it's called a nitration. So depending on what's on the ring, when you do electrophilic aromatic substitution, you call them an activator or a deactivator. So if whatever's on the benzene ring is a electron donating group, then that's called an activator. And if whatever's on the ring is a electron withdrawing group, then that's called a deactivator. And what activators do is it increases the electron density of the ring, and deactivators decrease the electron density of the ring. And this is important to know because electrophilic aromatic substitution goes through a carbocation intermediate. And so you can think about what increasing the electron density of the ring or decreasing it would do to the intermediate. Activators stabilize the cationic intermediate, deactivators destabilize the cationic intermediate. And these are some of the examples of activators and deactivators. And activators direct the incoming electrophile into the ortho-para position. Deactivators direct the incoming electrophile in the meta position, except for when the thing that's on the ring is a halogen, then it would direct it to ortho or para. And the first step in this lab is to generate the electrophile that we're going to attach to our rings. And we do that by mixing sulfuric acid and nitric acid. The lone pair of the nitric acid attacks the proton on the sulfuric acid. You get a nitronium ion, and so this is our electrophile. So we are going to nitrate acetylonide and methylbenzoate. So first let's look at acetylonide and the mechanism of how it works. So as you can see, acetylonide has an amide group, which is a electron donating group. So we know that it's going to be a para or ortho directing group. When the electrophile is added to the ortho or para of the amide group, the lone pair on the nitrogen, these nitrogens can be donated to the positive charge generated on the adjacent atom to stabilize the intermediate. So in this case, this lone pair is right next to this carbocation, and in this case, this lone pair isn't right next to a positive charge, but through resonance, it can get there. And by doing that, it forms an especially stable resonance contributor on which all of the atoms have octets. If the electrophile were to be added to the meta position, so if it were to be added either here or there, and if you were to draw a resonance structure of that, you'll notice that the lone pair on the nitrogen cannot stabilize the positive charge on the benzene ring. And so that intermediate wouldn't be as stable as these two intermediates. And now we move on to nitration of methylbenzoate. And as you can see, methylbenzoate has an ester group attached to it. And an ester group is an electron withdrawing group, which means that this ester group will direct an incoming electrophile to the meta position with respect to itself. So if the incoming electrophile were to be directed to the ortho or para position, you'll see that it will create this intermediate. And as you can see, this positive charge is right next to a partially positive carbon of a carbonyl group. And so that means two positive charges right next to each other, so that's a very unstable cation. And when the electrophile is attached in the meta position, you'll see that the positive charge is generated one carbon away from the partially positive carbonyl group, so there's no more positive repulsion going on there. As for the procedure, it's important not to put our hood sashes up, because if you leave it up, the hood is going to have a harder time sucking in the air, so you might breathe in the acidic fumes. And when you make an ice bath, you roughly use 50% ice and 50% water. so it's kind of like a slush. And it's also important to label your test tubes because the acids that we use are colorless liquid, so they all look the same and you could confuse them unless you label them. And it's important to keep the mixture cold. As for the reaction, you can pause and read all of the steps, but what's really important is to always add acid to water and not water to acid. And these are the calculations you're going to have to do on your lab reports. Welcome to your nitration of benzene lab. In this lab, we will perform nitration on 2 compounds, so we'll have 2 separate labs. First lab with acetylenide and the second lab with methylbenzoate. So let's get started on the acetylenide lab. First thing we're doing is measuring out 0.5 mils of nitric acid. So that's what I'm doing right here, and we're going to pipette them into a test tube. Then we're going to pipette out 0.6 mils of sulfuric acid. So I'm measuring that. And we're going to pipette them into a test tube as well. And then we're going to cool both of those acids in the ice bath for 15 minutes. After it's been cooled, we're going to add sulfuric acid dropwise to the nitric acid test tube, swirling the test tube every 3 drops of sulfuric acid. So as you can see, I'm shaking the test tube every 3 drops of sulfuric acid until I've added all of the sulfuric acid into the nitric acid test tube. After that, we're going to cool the mixture in an ice bath again for 15 minutes. So we have generated our electrophile. Now we weigh out about 0.5 grams of acetylenide and record this final number on the scale so that you guys can do calculations on it later. And we put that roughly 0.5 grams of acetylenide in a flask because we're going to add 1 ml of concentrated sulfuric acid to it. So here I'm measuring out 1 ml of concentrated sulfuric acid, and here I'm adding it to the flask that had the acetylenide in it. And we've prepared a hot water bath so that the acetylenide will melt in the acid, and you can give it a whirl if it's not melting and keep repeating that until everything melts completely. Now we add in the nitric acid and sulfuric acid mixture into the flask, and if you add it too rapidly, the mixture turns brown and it becomes difficult to purify later on, so you want to add it drop by drop. So here I'm measuring out 10 mils of chilled water. And we're going to add the reaction mixture to that chilled water. I'm just using that scoopula to prevent the star bar from going into the beaker. And you can see precipitation forming inside the beaker, and that is our product. And we're going to let it sit for 5 to 10 minutes to complete the precipitation. We then filtrate it by using suction filtration. This is to get rid of the water or other solvents by sucking them out through the filter paper. And I'm wetting the filter paper here with water. We're going to dump our content in there onto the filter paper. And then we're going to wash it with cold water to wash away the impurities. And this is what it looks like after it's been dried. Here I'm scraping our product into another beaker, and I dissolved it in some 95% ethanol using a hot water bath to dissolve everything. Cool it down in ice bath to reveal our crystallized product at the end. We're doing another suction filtration to harvest our crystals. Before we did the suction filtration, we weighed out the filter paper. And here I'm weighing our final product. Again, record this number to do your percent yield calculations. Getting our sample ready for melting point. This is the second part of the lab where we nitrate methylbenzoate. We're doing the exact same thing as before, but here we use methylbenzoate in place of acetylenide. So again, I measured out 0.5 mils of nitric acid and pipetted it into a test tube, and now I'm going to pipette out 0.6 mils of sulfuric acid and pipette that into the test tube as well. We leave both of those acids in the ice bath for 15 minutes. After it's been cooled, we're going to add sulfuric acid dropwise to the nitric acid test tube. And then we're going to keep this mixture in an ice bath again for 10 minutes. And we weigh out about 0.55 grams of methylbenzoate. And we put the weighed out methylbenzoate inside that flask before we added 1 ml of concentrated sulfuric acid, as you see me doing right there. We don't have to use a hot water bath as before because they're both liquid. We're adding the nitric acid and sulfuric acid mixture into the flask drop by drop. Here I'm measuring out 10 ml of chilled water, and our reaction mixture will be added to that water. Again, you see the precipitation, that is our product, and we're going to use a suction filtration. I'm scraping off our impure product into another beaker. I'm dissolving it in 95% ethanol in order to do a recrystallization. We're doing our second suction filtration in order to filter out our crystal, that is our pure product. I'm washing it with 95% ethanol to get everything out of that beaker.